I want to talk a little bit about the toothpick problem before we move on. I'm going to show you, just so we can review a little bit on how we can use our computer to help us. This is kind of where we left off the other day. What I did is I let my x value be the number of rows that were completed. Now, 1 second here. And then I said, so my y value was going to be, notice I put it in all caps, the number of toothpicks that got used, right? Started out with 250 of them, but I used 3 of them to make the first row. Then I used 6 more to make the second row. So if I made 2 rows, it took me 9 total. We talked about this, right? If I made 3 rows, it took me 9 additional plus the 9 I've already used. So now I'm up to 18 total. So my total is going to grow, and eventually I'm going to hit this line that I put in at 250. And when I hit 250, that means I've run out of toothpicks, right? So what I did is I said fit poly, and we did this when we did polynomials with, like, on the used car and on the square footage of the house and stuff like that, but we did polynomial of degree 1. Well, if I look at those dots, I can tell just with my eyeballs that those do not make a straight line. It looks like it's kind of on this upward curve, right? So you got to be a little bit clever, and you could figure this out a few different ways, but you can always just try different powers, 2nd degree, 3rd degree, 4th degree. You can always have your computer try it, and it only takes 2 seconds. But this one actually ends up being exactly a quadratic fit. Like, it's not a close fit, it's an exact fit. Okay? And you can see that it goes right through the dots just perfectly. So now, just using my eyeballs, you could have answered your Blackboard question, right? How many rows is it going to take? Or how many rows can I make? Well, I can for sure make 12, because 12, and I still have a little bit left over, right? Can I make 13? No. I'm going to run out, because I would need, it looks like, almost 270 or 280 in order to make 13. If I wanted to know exactly what it is, I can do an intersection of this line that I put at 250 and my curve, and it says 12.42. So I can make 12.42 rows, a little less than 12 and a half rows before I'm done. Now notice there's another intersection point way over here at negative 13 because it's a quadratic, but you just got to be smart enough to understand that we're not going to make negative 13 rows. So that point has no bearing on this situation, right? I'm only interested in the first quadrant. So that's one way to look at it. I want to show you another way that I think is even more clever and better, and I'm going to give props to Luke because this is what Luke came up with on Wednesday. Notice how he labeled his y-axis different than I did. I had no total number of toothpicks used, so I started at 0 and grew my way to 250. He said, how about we do it as total number of toothpicks remaining? So he's starting at 250, and then he's saying, well, if I make 1 row, it's going to take me 3 toothpicks to make it, therefore I have 247 left over. If I make 2 rows, it's going to take me 3 and 6, so I'm going to need a total of 9, therefore I have 241 left over. You could stop right after 2 points if you wanted to. You could do 3 points, you could do 4 points, you could do 5 points. It doesn't matter how many points you put in there. Once you do your computer to fit it, since it fits perfectly, it'll spit it out. So notice his equation's a little bit different. Mine was positive 1.5x squared plus 1.5x going up, starting at 0. His is negative, it's on this way down, right? So he's not interested where his graph hits 250. He's interested where his graph hits 0. Notice, exact same answer though, right? So 2 different ways to think about it. And I honestly never even thought of doing it that way, but I think that is even more intuitive than the way I did it. So I thought that was good. Comments or questions on that activity? Now, might you do a similar activity where the dots are not a perfect quadratic fit? Sure. Just like your used car didn't make a perfect straight line, it would be a miracle if it did, right? So you picked out the best line that fits the scattered data. The same thing could happen with a quadratic. You might have something that looks like a quadratic, but it's not perfect, but you can still do a best fit by doing the fit poly and then the second degree. Okay, what I'd like you to do is go to course docs and links, scroll down to section 5.1. Underneath the toothpicks, you will find Desmos penny circle. See it? Desmos penny circle. Watch the video, make your predictions, and I'm pausing you on step number 2 because I want everybody to see everybody else's data first.
Which one do I want to do first? These ones or the used car ones?
I don't care. Probably the used car ones.
I'm very certain I got the answers for all these. They're matching up with the other answer key just anyway.
I don't.
You don't?
But we can pound one out right after class.
Like I said, I'm very certain I got it. I've got some that matches mine.
And actually, I have to go straight up to the high school after class.
Okay.
So, but double check them, like GeoGebra and stuff like that. Maybe just do the used car one first. Okay.
Keep in mind, it's asking you to go for a range. Like, what answer do you know is too small? Be brave. What answer do you know is too large? And then you're just right. Just like, who am I thinking of? The nursery rhyme. Goldilocks and the Three Bears. One porridge is too hot, one porridge is too cold, one's just right. You're just right is going to be your guess. We are interested in how many are going to fit in the large carpet circle. The large carpet circle. And my gosh, do we have some variations here. So far I see one as low as 34. And I also see one as high as 750. So you guys are saying that the just right number is somewhere between 34 and 750.
You stack pennies on top?
Nope, they can't. They have, good question. Nope, they have to just be laid out on the carpet as he was doing it. Go ahead and make your guess. Okay, I'm going to let you start collecting data now. So on step 3, what we're going to do is we're going to work together as a team to collect data. So you can choose any diameter you want. Make it as big or small as you want. I think the largest you can do is a 6-inch diameter. And the smallest you can do is, I don't even know, 0.8. 0.8 doesn't even fit 1 penny. Once the penny turns dark, that means you got it in there. So you got to try to squeeze as many pennies as you can into whatever size circle that you chose. So if I choose like this size circle, 2.4, I'm going to see how many pennies I can get in there. Squeeze them in. Once you have some data, so like mine would be, looks like I can get 7 of them in there. So I would go here and I'd enter 2.4 is my diameter and 7 is my pennies. Do at least 2 circles. Do 3 if you're ahead of the game a little bit. As soon as everybody has at least 2 entered in there, I'll turn you loose on the next step. Did it tell us how large the carpet circle was? It will in a little bit. It hasn't told us yet. Do you guys agree that the carpet circle is larger than 6 inches? 6 is the biggest we can do here, right? Diameter. 6-inch diameter looks something like that. That carpet circle looks something like that, right? So what we're doing is we're using some smaller circles that are more manageable, right? Like I can quickly fill a 3.4 inch diameter circle and I can count the pennies. It's not too much work. But to fill that whole carpet circle, that would take a lot of work. So we're going smaller and easier so that we can gather data to hopefully make a prediction. Okay, it looks like everybody's got some dots in there. I'm going to let you go to the next step. The next step says to build a model. And you have to choose. Is it a line? Is it quadratic or is it exponential? Now, we haven't even talked about exponential yet. We're gonna when we get to the next chapter. So, exponential looks something like this, where it starts slow, and then eventually takes off and goes really fast. That's what an exponential growth looks like. So you need to determine which of the 3 you think is the best. And then you have to explain why you think that. Here were three suggestions that I just picked out. This one. Because it gets bigger and more pennies can fit into the circle. Does that tell you that it's going to be quadratic? Could you have chosen linear and given the same? Wouldn't linear also say, well, it gets bigger so more pennies fit in the circle? Would exponential growth also fit that description? So I think the description is accurate, but does that indicate to me that it's quadratic? Not necessarily. Because with every increase of size, you will slowly be able to fit more pennies. I'm critiquing these ones, by the way. Isn't that the same for linear and exponential? So I'm looking for you to be more specific here. I think it's quadratic model because it increases slowly. Some quadratics increase slowly, some quadratics increase quickly. Some lines increase slowly, like a line with a slope like that is slow, but a line with a slope like that is fast, right? So these were three that I kind of would say you need to be a little bit more clear about what you're talking about. I didn't see anybody reference the word area. Isn't that what we're doing? Don't we have some area of a circle? And we are filling that area. Think about painting it. Think about counting it up, measuring it. We're filling it with pennies, meaning we're seeing how big is the area and how many pennies can fit in that area. That's why we can't stack them. If we were stacking them, then we would be doing volume like a cylinder. But since we're only doing two-dimensional, so does anybody know the formula for the area of a circle? You would have learned it like in 7th grade. Pi times radius squared. Very nice. A equals pi r squared. If you were to graph that, what degree polynomial or what shape would it make? It's a quadratic because it's not x squared, it's r, but we're using r for the radius. So an area of a circle, as the radius increases, of course that's as the diameter increases as well, is going to be 3.14x squared. So what model is my best fit here? It should be quadratic. Yep. Okay, I'm going to let you move on here. Now they're telling you how big the carpet is. The carpet has a diameter of 22 inches. You should be able to now use the information you have to make a prediction of how large or how many pennies you think are going to fit. Feel free to use your calculator. Now, the accuracy of your guess is going to largely depend on how well you can get that red curve to fit over the blue dots. So be as meticulous as possible here. Try to be as precise as you can, getting that curve to go over the dots. So like yours looks a little shy. Can you see how yours is under the dots? Yeah. Go back to step 4. Whoops. Oh, there. Grab your red dot. Yeah, try to. There. Isn't that better? Yeah, there you go. That's going to make a huge difference. So yours is shy there too, Bailey. See what I'm talking about? See how yours is all under? Try to get it to go through the middle of the dots, and you can pull that red dot all the way up to the top. And it might make it easier. There you go. There you go. So what we're doing here now, you guys thought it was going to be between 34 and 750. You made some guess way back on the first screen, right? hopefully now you are making a more accurate guess, or if the guess that you're going with now is super close to the guess that you made at the very beginning, you might have made a really darn good guess at the beginning. I'm going to let you go on to step 6. Step 6 is going backwards now. The first one said, hey, your circle's diameter of 22 inches. How many pennies are going to fit? This one is saying, you have 2,000 pennies. How big of a circle would you need in order to make them fit? See how we're going backwards this time? It doesn't matter. It's in inches, right?
So the idea here is we have a 22, right? You estimated this when you started, but I don't think your calculation should be way down here because we're using this red line for a purpose. So scan up your eyeballs and see like how many, right? Or what you could do is you could just do the math on your calculator. Because what's X going to be? No? The inches. Right. So you know the carpet. They told you that the carpet one was 22, right? So you could just plug in 22, square it, take it times 1.34. Or you could just use your eyeballs.
Okay.
Okay, here was your, when you guys first guessed at it, you thought it was going to be anywhere between 34 and 750. Now that you guys have done a little math modeling, notice your guesses. It's still a decent sized range, 537 to 678. Why are they a little bit different? Because everybody made their red curve fit their dots just a little bit different, right? But notice the gap in our guesses is much, much smaller than it was at the very beginning. For the extension, notice how close these are. 32, 39, 38, 30, 38, 38, 38, 37, 39, 39. So a lot of you are really close because you had very similar models when you built that red curve, right? Okay. One more slide and then we'll reveal the answer on step 8. Step 7 is a very interesting question, so give it a little thought. The goal is to have as much money as possible. So when it says, would you rather, which one gives you more money? So lots of you are choosing nickels, which is interesting. Only one of you chose pennies. Why would you choose pennies? Do you guys all agree that a nickel is worth 5 times as much money? So we're good there, right? Do you guys know what's bigger area? A penny or a nickel? It's a nickel, but it's really darn close, right? So not a huge difference. So what's really the big factor here? This guy, you get a big circle, and this guy, you get a small circle. So the question is, does the fact that a nickel is worth 5 times as much money, does that make up for the fact that we're going with a smaller circle? That's the give and take, right? And almost all of you are saying nickels. So here's a question for you. You will be able to fit twice as many pennies in this circle as you will nickels in that circle. Yeah, true or false? Twice as many? Or another way to say that, this circle is twice as big as this circle. Is the 40 diameter circle twice as big as the 20 diameter circle? So if I had exactly two of these, exactly two of these would fit in here and fill up the whole thing. Somebody help us out here.
Probably just put in the equation to figure out the total area.
Yeah. Let's try it really quick. Pi r squared. Okay, for the 40, it would be pi, the radius of the 40 would be 20. So pi 20 squared, that's 400 pi. That's the area of my big circle. Do you guys agree? Now let's go to the small circle. It would be pi times radius. The radius would be 10, half of the diameter, right? Pi times 10 squared, which is 100 pi. Do you still think the big one is twice as big as the small one? It's not twice as big, it's 4 times as big. Does that change your answer? It's 4 times bigger, but a nickel is worth 5 times as much money. But a nickel is also a larger coin. It's not nearly as big of a difference as you think it is. And I've worked it out, and I've measured nickels, and I've measured pennies. And as far as I'm concerned, I think you come out just a little bit better on nickels. So those of you that went nickels, I think you're right. But it's not a slam dunk, right? It's actually really close. I figured out that this is just extra work I was doing because I'm a math nerd. I figured out that the pennies would be worth roughly $24.60, and the nickels would be worth roughly $27.80. So I'm making about $3.20 more going with the nickels. That's just a little side note. Okay, let's finish up here. Are you guys ready for the big reveal? Before we reveal, think now back to your original guess and to the one that you just calculated. So you got 2 guesses, your original and the one you just calculated. And let's watch to see how many there actually are. You can watch on your own or you can watch the screen. Could you imagine actually doing this?
No.
Like that would be awful, right? So I hope you kind of see the value of how... Now, okay, are we curing cancer here? No. We're figuring out how many pennies fit in a carpet circle. But I hope you can feel the value of using math to make a complicated thing easier. 663, original guess. Anybody have it? Who guessed 663? From the very original, who was the closest to 663? Anybody want to throw out a close guess? 550. Can anybody beat 550?
575.
575 is better. Anybody beat 575?
644.
That was really good. Who said that? Very good. Can anybody beat 644? That's really close. That's only 19 away. Okay, Kiana, you win nothing. You win pride. Now, when we actually calculated it, Did anybody get close to 663?
678.
678, not bad. 15 away. Only 4 away. 667. Can anybody beat that? You had 663? Right on the nose? Taya wins. Anybody else have 663? Taya, you win pride. Okay. Good. And I'm going to skip the last part of this activity because I want to let you out early today. So, here's what I'd like you to do. When you come back on Monday, your assignment, by the way, is a little different than any assignment that I've given you in the past. And you can certainly sit in this classroom and work on it for the next 14 minutes. I'm going to have you actually watch a video that I put together a long time ago that goes with the content that we're going to start on Monday. We went from straight lines linear, first degree polynomial, to quadratic parabola, second degree polynomial, and now we're going to talk about third and fourth and fifth and sixth degree polynomials. Right? That'll be like this on our graph. So what I did, underneath course docs and links, you'll see 5.2 and 5.3, polynomial functions and their graphs. I just like the way this old book that I used to use, it's an old college algebra book. It looks like this. If anybody wants to actually borrow the actual book, you can. It's right here. I just scanned a section from that book. Now, you could print this if you want. You certainly don't have to print it. But it looks like this. It's, 8 or 9 pages. And it's just got a few examples on graphing polynomial functions. Well, I go over these examples in this handy-dandy video that I made right here on YouTube. Now, it's 27 minutes long. It's a little bit longer than I had hoped it would have been. But your assignment is to just scan that, have that kind of open on the side, watch the examples that I go through on that video, and then there's a quiz right here. It's called 5.2, 5.3 video quiz. So the idea is if you watch the video, you should be able to get 5 out of 5 on this quiz. There's 5 questions. They're all true and false. You only get 1 crack at it. No redos on this one. Okay? So whatever you get out of 5 is what you get. So I encourage you to watch the video and pay attention and then try to get that. Have that quiz done before you come to class on Monday. And then Monday we'll cut out some paper and build some boxes. All right. See you on Monday.